Hey students, welcome to our last round of this video, ELT 110. I would say that I'm sorry to see it go, but I'm not. Talking to y'all through video stinks by comparison to having an actual class. Nonetheless, I do think that you will have learned stuff about circuits. This is not the greatest way in the world to learn. But if you've been going through the book, then you are learning a lot of material. You'll have seen stuff. I think the projects that we have come up with a way of giving you a little hands-on experience with the types of things that we're talking about. Is it perfect? No. But I think that it'll work. It'll work. I think you'll know stuff about circuits. The last project I think should work really nicely, and the final project, which I will have posted up on the webpage, and the capacitors. It's been fun to see people's capacitors. In particular, it's fun to see Blake's the only person who has an analog meter, and it's fun to watch the needle on his little video. So this hasn't been a great way to have a second half of a class, but we've managed to get through it. And but I'm not sorry to see it go. Okay, so let's talk a little bit about transformers to wrap this up. So a transformer, to answer people's questions, or remember, what is a transformer? Transformer is two coils, two solenoids. And remember that a solenoid, if you run electric current through a solenoid, it will produce a magnetic field. But a solenoid also is a thing that if you run a magnetic field through it, you will induce a voltage in the solenoid. So the idea of a transformer is you have one solenoid that induces a voltage in another solenoid. And the amount of magnetic field produced and the amount of voltage induced in the other, so the amount of magnetic field produced by the first solenoid and the amount of voltage induced by the second in the second solenoid depends on the amount of loops in each solenoid. So this would be, this is my primary solenoid. And then if I had another one, this is a secondary. Then if I run current through here, I get a magnetic field generated in this solenoid. That magnetic field goes through this solenoid, and I get voltage out here. Now, so first thing, several people asked about electrical isolation. That's a cool thing about transformers and induction. These two things don't actually touch each other, okay? You can, now if you interwound the two wires so that these were right within each other, they still wouldn't have to touch, but then you really get the magnetic field of the one going through the other. This can also be done by using a ferrous material to guide the magnetic field of the one through the other. But they don't touch. Right? If you hooked up a meter, if you hooked up a resistance meter, an ohm meter, to the one and to the other, there'd be no kind of connectivity. So using a transformer takes these two things and isolates the two sides of the transformer are electrically isolated from each other. There is no direct conductivity, which means that a transformer will not pass a DC voltage. Okay, remember that induction only works when things change, and in DC, nothing is changing. So there'll be no induction. And so these two things won't do anything with a DC circuit. But an AC circuit, they will. And since they're since they are electrically isolated from each other, you don't get, well, if it's not broken or something, you don't get any kind of shorting or direct action between it, which can, you can think of a variety of ways that might be useful. Someone said, okay, so the ratio of the number of turns in the primary to the secondary determine whether the voltage goes up or down between the two coils. And so they said, is there ever a case where you would want to have equal number of coils so the voltage doesn't go up or down? And I could think yes, and that would be if you only wanted your transformer to serve the purpose of electrically isolating one part of your circuit from another part of the circuit. Okay, so that if you got some big DC current surge through one, it wouldn't be transferred over to the other. Okay, so I can envision a case where you would have equal numbers of coils in both. Another student asked, well, if it's the same power in as power out, what's the advantage to the transformer? And the answer to that question is that, well, you get more voltage out or less voltage out, depending on what you want. Now, why would you care about this? Well, because if you want to transmit power at low voltage, you have to use high current. And so high current will produce a lot of heat through resistance. So if you run a high current through a wire, then you get a lot of resistive heating. So you will lose power due to heat if you have high current. So if you want to transmit power across a long distance, you run the voltage up really high. So you transmit the electrical power at high voltage with very little current. So you have lots of voltage, little current, and you don't get a whole lot of heating of the wires. Okay, so you don't lose power to heating. So it's more efficient to transmit power over long distances at high voltage. Now, you do lose when you have this. There is always heating in the transformer. And so a transformer will always have a certain inefficiency. So you never actually get all the power out that you put in. So you have a balance between you're going to lose some power at the transformer that you might, but you're going to gain. You're going to reduce your losses when you transmit over distance if you have high voltage. So there's where you get into your engineers and stuff, where your engineers are calculating out like, okay, we're going to go this much distance. How much loss do we get to heating from the wire? How much loss do we get from heating in the transformer? And you work that out for like what's the optimal setup for your to do this. Okay. All right. Okay, I think those are the main things that people have asked about. I'm going to pause here for a minute, and there's a couple of questions that a lot of people asked. We'll do those and see how we're doing on time for some of the other example problems. All right, so probably the thing that most people asked about was example 14.2. It says 2 coils are wound on a single core. Okay, so here's my core. I have my primary core on. I have my secondary coil. All right. And it says the coefficient of coupling is 0.3. And then it says the inductance of one is 10 microhenries and the other is 15 microhenries. Okay. So the mutual inductance is Lm equals K square root of L1, L2. So 0.3 square root of 10 microhenries times 15 microhenries, 0.3 times the square root of 150 microhenries squared. Microhenry times microhenry being microhenry squared. So run this through my calculator. 150 square root is 12.25. 0.3 times 12.25 microhenries, since square root of microhenry squared is microhenries. Then 0.3 times 12.25, take that, times 0.3, and I got 3.67 microhenries. And that's what the book's got. Make my calculator go away for a minute here. Okay, so that's what I have for the book. All right, now the related question says find the mutual inductance when K is 0.5, L1 is 1 millihenry, and L2 is 600 microhenries. Okay, so this one's a little more tricky. Here I took microhenries times microhenries. I got microhenries squared, and I took the square root of microhenries, gets me back to microhenries. I got to have the same units, or I won't be able to have like the square and then the square root. So I'm going to turn this one into 1 millihenry is 1,000 microhenries. So now, mutual inductance would be 0.5 times the square root of 600 microhenries times 1,000 microhenries, which is 0.5 times the square root of 600,000 microhenries squared. 0.5 times the square root of 600,000 microhenries squared. So first of all, I got to figure out what is the square root of 600,000. 600, 1, 2, 3, 1,000. Square root of that. 774.56. So it's 0.5 times 774.6. Square root of microhenries squared is microhenries. So then I get this is going to be half of that. So divide that by 2, and I get 387 microhenries. Now I need to check in the back of the book and see if that's right. And yeah, I checked in the back of the book, and they also or the end of the chapter, I should say, and they also get 387 microhenries. So that's the example 14.2 and the related problem.